Good afternoon, gentlemen. It's core afternoon, but can't afford to miss this lesson on solar cells. We've got precious few lessons left, so let's have a go. Solar cell, photovoltaic cells, not the type that warm your hot water, but those type that make electricity, consist of a p-n junction. You should be familiar with this. Basically, silicon doped on this side here, doped with boron to become a P. So its holes are our free conductors here, our charge carriers here, sorry, and the N-type semiconductor doped with arsenic, and here's our extra little electron here. So it's electrons or N negative charges that are our charge carriers here. And they're going to bounce around and move around because of thermal energy. Whoop, plop, it's going to fall across that junction and fill that hole, which is going to give rise now to a depletion zone in the middle because we've depleted the charge carriers. And so the hole that existed here doesn't exist anymore, and the free electron that existed doesn't exist here anymore. And that's where everything would stop. That's what happens when we just make a p-n junction at the factory. We join the two together, and we get this depletion zone occur in the middle. No one's got any energy. We've got no free charge carriers, no electrons here in the conduction band of energies, and none over here. And those holes can only move if an electron moves across into it. No one's going anywhere. Until, of course, we apply our little photon of light. And imagine that that photon of light hits that electron there. It can hit any electron, doesn't matter which electron it is, but let's just assume that it hits that one there. What's going to happen is it's going to give it kinetic energy. This little electron, if I can pick up the electron, here we go. It's there we go. It's going to buzz around with all this kinetic energy, and it's probably going to get shot across the membrane, the junction. It may or may not. It's actually most likely to. And let's go back to thinking what happened in the depletion zone as to why that must be most likely to go across to the right. And that's because when this negative charge moved away from this type here, which was electrically neutral, we've lost a negative charge, and so now this side of it becomes slightly positive. And likewise on this side over here, because we've got an electron that we didn't need, because boron's only got one less proton, so we didn't actually need that electron, it's going to make that side negative. And so now when this electron gets kinetic energy, on average, it's actually kind of more likely, to move across onto this side here with a whole lot of kinetic energy and sort of end up flying over into this region somewhere here. And so now I've got charge carriers back again here in the whole of the silicon, the photovoltaic cell, and some holes over here. Now, to understand the external current flow, we're going to do what we did before, and that's we're going to simplify the whole diagram a whole lot more. We don't want to see all the individual atoms and elements. We just want to know that there's holes, which are our charge carriers in the p-type, and that there's electrons that are charge carriers in the n-type. And the way that we make solar cells is the n-type is very, very thin. It's also just got a little mesh of wires over the top of it so that the photons of light can get through the wires, whereas the back is a solid plate of metal connected to a much thicker section of p-type semiconductor. So a photon of light is just much more likely to interact on the p side because it's much thicker. The n side is very, 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 very thin indeed. It's a tiny, thin wafer of material there. So what actually happens, remember we form the p-n junction, and our charges are going to move by just kind of random energy, thermal energy, across onto that side. And so now we've got this depletion zone here where we're depleted of charge carriers. It's a bit of an insulator. And of course, that's going to set up an electric field where this is negative and that's slightly positive. This has lost its electrons. This has gained some extra electrons. As I said, that electric field is really, really important. Then what happens is along comes a photon of light. It can interact with any of the atoms in that doped silicon. And remember, whichever electron it interacts with, it's going to create a whole electron pair. So even though there wasn't, what we haven't done is we haven't drawn all of the whole electron pairs, because that would be drawing the whole material, because every electron's in the valence shell is sitting in a hole. Okay, so let's say it hits that electron there. It's going to give it some kinetic energy. The electric field is going to mean that it's going to be wanted to be more likely flung across this way, and it's going to push on that electron, which is going to push on this electron, and maybe that electron ends up in the metal, the actual lattice of the metal now. And now, because that's going to put a bit of a force on all of them, an electromotive force, a voltage. It's going to cause all of the electrons to want to move around, and lo and behold, we've got an electric current starting to flow. And of course, now we've got more holes on this side here. Okay, the holes are going to migrate across, and our electrons that are, of course, being pumped in this. I'm just going to flick this guy up to here, but remember they've all sort of moved around one. This guy's going to fill that hole, and of course, in our diagram, an electron hole pair, we just don't draw them, okay, because everything's an electron hole pair, so we don't need to draw those electron holes anymore. Of course, that photon of light ceases to exist because it's given its energy to the electron, and the current stops until another photon of light comes along and hits an electron sitting in this potentially in the depletion zone, because that's where the electric field is going to be the strongest to fling it across this way, and it's going to bump into this one, which is going to kind of bump into that one, it's going to bump into this one, it's going to knock this one into the better metal, and these guys are going to go rack off, we're negatives, we don't like you very much, and everyone's going to roll over, and it's going to push the electrons around in that circuit. And so in this way, the energy contained in the photon of light gets transferred by the photoelectric effect to kinetic energy of the electrons. Because of the setting up of the electric field, they're going to fly, more likely to fly into the N-type conductor, where they're going to push electrons so that they end up slamming into these little lattice of conductors stuck on the surface of the N-type silicon. Let's get rid of all that, and that's going to cause an electric current to flow. That, watch it as many times as you like, is how a photovoltaic solar cell generates a current in the external field from the energy from